way around the board.
Oh, we don't check.
League roll down.
Yep.
So does anyone have any questions over 11-2 homework? If you kind of notice where we're at in the calendar, so we were kind of ahead of schedule. It only took us one day to do 11-1. Anytime I give you back a test, I never really know how long it's going to take to talk about the test and go over that and then introduce the new material. So I budgeted for 2 days for 11-1. It turns out we only really needed that 1 day. And I went ahead and introduced 11-2 on Monday. So I'm on schedule to do 11-3 today. If we can get through 11-3 today, I'm comfortable giving you guys a work day on Friday, meaning do your homework, and then I can answer any questions you have over 11-1, 11-2, or 11-3 as we come back that Wednesday. So Monday, campus is closed because of President's Day, and there's also some things going around campus, staff development work day and stuff. So I won't see you until Wednesday if we get through 11-3 today. So good plan with that.
You have to go to lecture on Tuesday?
Do I have to go to lecture on
Yeah,
Tuesday?
sometimes
No, I
they
don't.
Sometimes
I'm
they
an
have.
adjunct, so yeah, and not that I've heard of, but
That's a plus.
yeah, I have to do enough of that professional development type stuff through the other universities I work with, but no, I don't. So does everyone feel comfortable with that? I will be on campus. I teach another class right after this one, so I will be on campus. I will probably be in the adjunct's office. If anyone has any question, you can look at that on the schedule. So if you want to stop by and go over homework, if you're on campus already, feel free to do that. I don't know, as you know, we get closer, I think we're on track to do that. So just give you that Friday to work on your assignments. So today we're going to introduce a concept you guys have probably come across before, and it's basic probability. So this is 11-3. And in mathematics, mathematics and statistics and science, there's really two types of probabilities we talk about. We talk about classical probabilities, those are your mathematicians, your statisticians, and then empirical probabilities, and those are your scientists that run experiments. Ideally, the empirical probabilities are going to approach the classical probabilities if you run the experiment for long enough. So probability experiment, we're looking at the process that leads to a well-defined result called an outcome. An outcome is a result of a single trial of a probability experiment. So if I flip a coin and there's only heads or tails, then I have well-defined results. I'm either going to get heads or I'm going to get tails. And an outcome would be flipping it and getting a head, right? Eventually, we're going to talk about what's the probability of a specific outcome, or what's the probability of rolling a dice, what's the probability of getting a number greater than 3 or less than 3. And so we'll have to add up those types of probabilities. You guys have all had experience with this, right? At some point, maybe middle school or high school come up, or just in life, you've heard the word probability before. Some of the terminology, we use sample space. So sample space is kind of like the universe, all possible outcomes. That's going to be your sample space. And then an experiment would be a subset of the sample space. So getting kind of that lingo we got from chapter 2, that's going to kind of come up. An event is any subset of a sample space. So an experiment would be out of 52 cards, drawing 1 card. Sample space is going to be the 52 different choices you have. And then the event would be getting an ace. So you say, what's the probability of getting an ace? And that's the kind of way we're going to word it. So probability is the number of elements in the outcome divided by the number of elements in the sample space, right? Makes sense. How many ways can I get an ace? I can get an ace of hearts, ace of diamond, ace of club, ace of spades. So I have 4 different elements in the event getting an ace. Out of the total number of outcomes in the sample space, which is 2. So a little bit of this is exposure. If you know nothing about cards, and I say, you know, what's the probability of getting a face card? You need to have a little bit of exposure of how many face cards are there in a deck, how many cards are in a deck. So as you get exposure to this, you'll start seeing. And if anyone has any questions, we'll go over them. Plenty of time for the exam. There's one key assumption that we make in classical probability, and that's every outcome in the sample space is equally likely. And that's not always true in the real world. You know, if we have a weighted dice, then the outcomes are equally likely. But we assume in classical probability that the probability is evenly distributed. So there's 52 cards. Every card has 1/52 chance of being drawn. So let's look at our first example here. A single dice is rolled. Find the probability of getting a 2. 1/6, right? This is classical probability. It's a single dice. There's 6 sides. There's a side that's 1, 2, 3, 4, 5, or 6. So this kind of goes into a little more detail, but it's saying in this case, our sample space looks like 1, 2, 3, 4, 5, and 6. There are 6 outcomes, so the number of elements in sample space is 6. One possible outcome gives us a 2. So the number of elements in the same or in the event getting a 2 is 1 out of 6. Did the sign-in sheet go around? What about a number less than 5? 4 out of 6 is the same as 2/3, right? So
do you want us to use like P parentheses a number less than 5 for like the official like on the homework, or
no, you don't have to.
and on the test, do you not want us to do that either?
No, you wouldn't necessarily. 2/3 would be fine, or 4/6 simplified. Ideally, it's nice because obviously they're going to get a lot more complicated. It's not going to be as straightforward. One like this, I might say, what's the probability of getting a number less than 5, and write it that way, and then said equals what.
Oh, okay.
A lot of times these will be like, what's the probability of event A happening? A is getting a number, getting a 2. And then I will have part A, what's the probability of A?
Okay.
And I might say, what does A look like? What are the elements in A? What are the elements in S? So S would look like 1, 2, 3, 4, 5, 6. In this case, let's call it B. B is a number less than 5. So the probability of B, I don't really care the way the book writes it because it writes so much out. When in math we like to use shorthand, we like to use notation. If B is defined as this, I only care about the probability of B. Probability of B are the number of elements in B over the number of elements in S, which would be 4 out of 6, which is 2/3. Something like this is a little, versus if you had to write out the numbers, if you had to write, they call this E every time, which I don't think is clear as saying, okay, this set is called B, this set is called A, this set is called C, and the probability of B happening. Most of the times these are going to be multi-part problems.
Okay.
So in that case, it's going to make more sense to kind of use a shorthand. If it was just a problem like this, and you said 2/3, that would be fine. If you said 4 or 6 equals 2/3, your book's going to want you to simplify. So if you look at the back, and you say, I didn't get the same answer. You might have, it just might not look the same.
Okay.
What's the probability of getting an odd number? 1/2, right? So a little bit of exposure, you need to know a little bit about odd numbers, even numbers, face cards, hearts, diamonds, spades, and like I said, you'll have more exposure to it. But you can always go to Google and say, you know, how many face cards are there? How many hearts are there? How many diamonds are there? How many spades are there? You know, what's a 52 card deck look like? And that gives you some exposure to that. Okay, so this is another example where writing out the sample space might come in handy. When we think of a dice, we know it has 6 sides. We think of flipping a coin, we know there's 2 sides, right? So if I flip 2 coins, how many outcomes do I possibly have? So this is kind of that counting game.
So here's my question on that, because you can get 2 heads, 2 tails, or twice you can get 1 head, 1 tail. So does that become 1 time since there's?
So here's a good way to think about it. I have 2 coins. How many choices do I have for my first coin? It can either be heads or tails, right? 2, right? How many do I have for my second coin? 2. So I should have 4 total outcomes.
Even if they're the same, like this one would be heads,
yeah.
would be tails.
So you would only list it once because you're flipping them at the same time. So order doesn't matter here.
Okay.
So if I have 2 coins and I toss them, then I need my sample space. My sample space looks like heads, 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 tails, tails, heads, tails, tails. So order matters, but heads, heads, you can't tell what. If I flip 2 coins and get heads, heads, it doesn't matter which one was first or which one was second. It's the same group. But if I flip heads, tails, that's different than tails, heads, because they're unique. They're different. You can tell the difference. The heads, tails is different than tails, heads, but heads, heads is the same as heads, heads, right? It's kind of by like the repeats. You know there's going to be 4 in the group, and these are the only options you have.
So you have to write those.
Well, this will help answer these questions. Anytime you want to visualize the sample space, what are all possible outcomes? I can either get heads, heads, tails, tails, or heads, tails, or tails, heads. But if I get heads, heads versus heads, heads, that's the exact same group, right? Tails, tails, and tails, tails, that's the exact same group. So the order here, if they're like, you have to kind of only pick the one. But if it's heads, tails, that's different than tails, heads. And if you think of the 4 different choices, this is either heads or this is tails, this is heads or this is tails. So if I kind of pair it, and this is something we're going to talk about in the next section. Oops. Oh, I'm going the wrong way. Sorry. This is something we're going to talk about when we get to tree diagrams, and tree diagrams can help you visualize what's going on. For my first choice, I either have heads or tails. For my second choice, if I got heads, I have heads or tails. And if I would have gotten tails, I have heads or tails. So I have heads, 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 tails, tails, heads, or tails, tails. That's called a tree diagram. We're going to do some more of that in some more advanced cases. But here you can see that there are 4 different outcomes, and they're heads, 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 tails, tails, heads, tails, tails. If I would have continued on and said I'm flipping 3 coins, then I would have had 8 outcomes, and it would have been heads, heads, head, heads, tails, head, tails, heads, head, and there would have been 2 more choices here. So sometimes tree diagrams can come in handy coming up with sample spaces. If I say I'm rolling 1 dice and flipping 1 coin, I have 6 choices for my dice and 2 choices for my coins, so I have 12 possible combinations, 12 possible outcomes. So coming up with them would be 1 head, 1 tail, 2 head, 2 tails. You guys kind of see that? Visualizing the sample space is beneficial to answering the question. What's the probability of getting 2 heads?
1 head.
Getting 2 heads. 1/4, right? There's 1 outcome in my sample space that has 2 heads out of 4 total outcomes. And in classical probability, we assume each outcome is equally likely, right? So what's the probability of getting at least 1 head? 3/4, right? Because the at least means 1 or more. So this would be 1/4. This would be 3/4. And the probability at most 1 head? At most 1 head. 1/2? It would be 3/4 as well, because at most means 1 or less.
Oh, yeah.
Yeah. Yes. So like I said, that at least and at most, those words are going to come up. And at least means one or more. At most means one or less.
So even the zero, like the tails.
Yes, even that if I said at most you can get is one head, the tails would be in that event because it has at most one head. At most means the number or less. So we had both of those 3/4 there. So sometimes when you go to take the exam, it's a really good idea to kind of circle those key words like at most and at least. And kind of put a star there to be careful the way you do that. So the notation here, being able to come up with the sample space, you could do the same thing with 3 coins and come up with a larger sample space, but answer the same type of questions. So some things about probability that comes up, that both the number of elements in E and the number of elements in S have to be 0 or positive. We never talk about negative probabilities. Probabilities are always between the number 0 and 1. You can never have something greater than 1 or something less than 0. So if we talk about, you can almost think of this as like the percentage of times it's going to happen. You think, oh, 50%, that's the probability of 1/2. 3/4. You're always in between 0 and 1. If the probability is 0, that's an impossible event. What's the probability of getting a 7 rolling a 6-sided dice? 0. It's impossible. What's the probability of getting a number less than 7 rolling a 6-sided dice? That's 1. It would be 6/6, and that's called an uncertain event. Right? And then just kind of looking at it, if it's less than half, we say it's unlikely. If it's greater than half, we say it's a likely event. It's never greater than 1. So recall when we had the sample space, if we have an event and then we have the complement of that event, right? If I say the probability of getting an odd number, what's the probability of getting an even number? If you add those two probabilities together, you always get 1 because every number is either even or odd, right? And there's no overlapping. They're two just joined events. So if we talk about the event, my pen here, the event E and the event where E doesn't occur. Okay. So what's the probability of getting an odd number? Let's say that was 3/4. And so what's the probability of getting not an odd number? That'd be 1/4 because 3/4 plus 1/4 has to equal 1. So you can talk about what's the probability of not an event happening. That's going to be 1 minus the probability of the event happening. Okay? The sum of the probabilities of all the outcomes in the sample space will always be 1. So if I look at this example, the probability of getting just a 1 is a 6. A 6, a 6, a 6, a 6, a 6. If I add those all up, I get 1. So these are kind of like the elements in the sample space. And the probability of each individual element happening is going to be, if you add those probabilities up together, it's going to always add up to be 1. And that's kind of where I was talking about. Eventually, we'll get to these tree diagrams. And if I have heads or tails, this has a probability of 1/2. And this has a probability of 1/2, right? And the sum is always going to add up to 1. And if I go through, and we're going to have a whole section on tree diagrams. These happen to be equally weighted, but I multiply the branches, and each outcome is equally likely. This is probability of 1/2. This from getting heads the first time doesn't affect getting heads the second time, so it's probability of 1/2. So the probability of getting heads is a 4th. There are 4 outcomes like that, and if I add up any branch here, I always get 1. And if I add them up here, I get 1. So this is going to come in handy when we talk about conditional probabilities, where the first condition affects the second condition, and we'll look at the probabilities. But the rules of probability always remain the same. The sum of every outcome has to add up to 1. Here's the example where I was talking about the event E and the event not E. So if I were to find what's the probability of getting a 4, a 4 will not occur. What's the probability of 4 will not occur? So any number other than 4, I would write that as a probability of not getting a 4. And I know that's going to be 5/6, but I can also say it's going to be 1 minus the probability of getting a 4, which is 1 minus 1/6, which is 5/6. So in this section, the facts about probability are going to be pretty transparent, but eventually they're going to be, maybe it's impossible or really hard to calculate the probability of getting not a 4, but it's easy to calculate the probability of getting a 4. So you can calculate it by using this rule. Famous problem, it's not in this book that I've seen before, is saying, what's the probability that 2 people in here share a birthday? It's really hard to calculate, but I can find the probability that no people in here share a birthday. It's really easy, and then take 1 minus that. And then I'd have the probability that at least 2 people share a birthday. This is what I was talking about, empirical probability, and these are kind of what scientists do based on observation or observed frequency. Mendel, what's his first name? Gregory Mendel did the famous pea pod experiment where he took snow peas and he crossed them with white and red, and he saw which one was dominant, which one was a recessive gene, and he did his experiment long enough, came up with the Punnett square and said the probability or the outcome, is 1/4 to 3/4, and then he showed that in his experiment. And there's a lot of kind of controversy whether he kind of forced the data to be the classical data to say that this is the reason why behind it. He knew what the outcome should be based on if it's recessive or dominant, and then he ran his experiment to show that. But that's just an example of the observed frequency. So we don't really calculate empirical probabilities in here because we do the classical mathematical approach. We don't have you flip a coin 500 times to see what's the empirical probability that coin's going to be heads or that coin's going to be tails. There's the theory of large numbers that says if you do an empirical probability long enough, it's going to approach the classical. If I flip a coin 3 times and I get 2 heads and 1 tails, and then I make the assumption that 2 out of 3 times this coin's going to get heads, that's not a very good assumption. So if I run that experiment for really long periods of time, that number is going to get closer and closer to 1/2. The probability of getting heads over tails is going to be closer to 1/2. This is used a lot of time in data collection, but let's look at this example. We have 500 people, 21 have type O, 22 have type A blood, 5 have type B blood, and 2 have type AB blood. Set up a frequency distribution and find these probabilities for a person selected at random from the sample. So what's the probability a person has type O blood? 21 out of 50, right? So this is the empirical probability using the data. What's the probability a person has type A or B blood? A or B. You can't have both A and B unless it's AB, but yeah, that's gonna come up because it will be the multi-stage kind of experiment. What's the probability someone has type A or someone has type B? So in this group, they have A or B, but not AB.
Okay, so you don't count the AB then?
You don't count the AB because that's a different type.
Okay. Yeah.
Right, so that would end up being
27 over
27 over 50. What's the probability a person has type A, has neither type A nor type O blood? Neither type A nor type O. So we have 5 with B and 2 with AB. 7 out of 21. Or sorry, 7 out of 50. Where did I get 21 at? If they have neither type A nor type O, that means they have to have type B or type AB. Right? Because there's 4 blood types. What's the probability a person does not have type AB blood? 48 out of 50?
Yeah.
So here, you could say if they don't have type AB, they have type A, type B, or type O, and you could add those 3 together. Or you could say 2 people have type AB, so 48 have to have not AB. You see that approach there?
Do we need to reduce that?
Yeah, well, yeah, you can simplify. Question?
In process in my head.
The AB,
The C one.
the C one, this 7 out of 50. If it says neither type A nor type O, that means they have to have type B or type AB. So you would add those 2 numbers together.
Now, in a thing like this where it's actually people,
Mm-hmm.
would you want us to simplify it, or would you just want us to make it?
So yeah, of course you'd simplify this. What would this be? 24 out of 25?
Do you always want us to simplify?
Yeah, your answer in the back of the book is going to be simplified. You guys have calculators, and your calculators can reduce fractions, so they'll just help me grade it that everyone has the same answer. Here, I would like to see you write 40 out of 50 so I can see where that came from and then simplify that to 24 out of 25. And I think your book even.
So is that the frequency?
This is called the frequency diagram. You might be asked to draw one of these where you have your type and you have how many times they show up, the frequency. So out of 50, I can see 22 are A, 5 are B, 2 are AB, and 21 are O. It's kind of arranging the data in a nice little chart where it's easy to read. There's nothing new here except taking out all the middle words and rearranging it nicely. Where I can see 22 people have type A, 5 people have B, 2 have AB, 21 have O. In statistics, they do population samples, and then they extrapolate that data for larger sets. So then they say, if I type everyone in here, your blood type, then I might make an assumption on what percentage the campus has type A blood. Right? So I don't know what everyone's percentage is. I just do a small sample space, and then I can extrapolate that to saying, if there's 10,000 people on campus, and 25% of my class has type A blood, I'm assuming this amount on campus has the type A blood. That can be a little misleading when you don't have a very good representation of your sample space. That gets into the statistics of it. We kind of stay out of that for this course and just talk about the math of it. So if I go back to the homework in this section, the problems that I assign. 1, 3. Yeah, the page numbers. So when I first, I was not aware the edition changed when they gave me this course from the 2nd edition to the 3rd edition. So the page numbers are from my 2nd edition. I have yet to receive the 3rd edition book from the department chair. He's out on medical leave. So I just got it offline as like e-access. So I didn't even know until like the day of class, everyone had a different book. So yeah, it kind of ignored the page. Hopefully at this point you can pull your book and say, 11-3, the homework starts on this page. So I apologize about that. I might work on fixing it and uploading a new one. So 21 through 31, odd. So 21 through 31, odd. 11.3. First, it asked to describe whether it is an empirical probability or a classical probability. Probability of randomly selecting state beginning with the letter A. 2 out of 25. Alabama, Alaska, Arizona, Arkansas. There's 4 of them out of 50, which is 2 out of 25, which is the classical probability. One school, 59% of the students having lunch in the union are women, so the probability of randomly selecting a student from the campus phone directory being male is 0.41. That would be empirical because it's in a specific case. Pool table, 15 balls, labeled 1 through 15. Probability of a ball made on a break having a number less than 6. This is the third. So that is classical. 23, a dice is rolled 1 time. Find the probabilities. This is very similar to what we did in class. We have 1 dice, we have 6 outcomes. So what's the probability of getting a 4? 1/6. What's the probability of getting an even number? 1/2. What's the probability of getting a number greater than 4? 2/6, which would be 1/3. Getting a number less than 7? 1, right? 6 out of 6, which is 1. Getting a number greater than 0? 1. Getting a number greater than 3 or an odd number? 5, 6, right? So this is, if we write out that sample space, 1, 2, 3, 4, 5, 6, getting a number greater than 3 would be 4, 5, 6, or odd would be 1 or 3. So 5 out of 6 would be the correct answer there.
I thought it was talking about an odd number higher than 3, but not.
Yeah, it says
Or.
Yeah, getting a number greater than 3 or an odd number. So what's the probability of, so here we have or and this one we have and. What's the probability of getting a number greater than 3 and an odd number? 1/6, right? Because 5 would be the only outcome. So if I look at my sample space, 1, 2, 3, 4, 5, 6, getting number greater than 3 and an odd number. So these are the ones greater than 3. This is the only one that's odd.
Or you can do it the easy way and just say it's the same as 6, except for they put the and instead of the or.
So you have
5 and 1 equals 6. So 6
that's
over
not
6
going to
over
always be,
Well, no,
Yeah.
but in that instance.
yeah, but you don't want to think that way because here, this is getting a number that's not greater than 3 or an odd number is 1/6 because 2 is the only one that's not greater than 3 or odd. So if it listed it that way, you could think of that. But this is different because it says and. It's not the complement of it. It doesn't say not. You're thinking of, I say, if the probability of getting an A in this course is 1 out of 7, what's the probability of not getting an A? 6 out of 7, right? That's the way you would do it. When I say what's the probability of getting a B, that has no reflection on the probability of getting an A necessarily.
Right, but they're asking the same thing, right?
They're not. These are 2 different groups. This is the outcome. The event in this case looks like 1, 3, 4, 5, and 6. And the event in this case looks like 5.
Because it's and.
And. So they have to both happen.
Right, but what I'm saying is if you take both of them together, 1 equals,
I think it's just.
Yeah, it's just a fluke, that 1/5 plus 4/5. What is it? 1/6 plus
plus
5/6 is 1. Yeah,
Right.
it's not because the and or the or. That's not going to happen necessarily. It's just a fluke that happened. It's not going to always happen. When that happens is when I say something like, the probability of event E happening is 1/6. What's the probability of event not E happening? Those two added together is 1. But this is saying getting a number greater than 3 or odd, and this is getting a number greater than 3 and odd. 5 is in both these outcomes. So they're not complements of each other. I think you're just trying to make a connection that's not necessarily there. The couple has 2 children. Find the probability both children are girls. At least one child is a girl, both children are the same gender. This is just like the quarter flipping one, right? Instead of heads, tails, it's girls, boys, right? There's 4 outcomes, either girl, 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 boy, boy, girl, or boy, boy. The Price is Right game show contestant spins a wheel number 1 through 7 with equally sized regions. So very much like the dice problem, except there's 7 outcomes. What number was this? 25, 26? The list contains names of 5 and anthropology, thank you, students, 2 science, psychology students, thank you, sociology, I can't talk, 3 psychology students, thank you. So what's the probability that students chosen at random fit these categories? So just like the blood type problem, you have to be careful. So there's not at least or at most here. 7 women and 9 men. What's the probability is selected at random, come to the board? What's the probability the student's a man? It's an empirical probability kind of example.
So would it be like, so would you do like,
It would be 9 out of
so 16
16.
total, so 1 out of 16, or would it, you do like?
What's the probability it's a man? Well, there's 9 men to
9 out of
choose.
16?
9 out of 16, which would that simplify? I don't think so.
Which is kind of the same thing on 27, it's like 5.
Yeah, 27. Yeah, find the probability that the system is a we. So if you have the different categories. This 33. So in a survey, 16% of male college students say they lie sometimes to get women to go out on a date with them. If a male college student is chosen at random, find the probability that he does not lie to get a date with a woman. So if you know 16% lie, what percent? Yeah, doesn't lie. So this is that idea of that the event something happening and the event something that something does not happen. Those will always add up to 1, right? So any of these are kind of free game for test type questions. We're going to get into more difficult type of problems. In 11.4, we're going to talk about tree diagrams. An example of tree diagrams, like I said here, here's an example if you have 3 children, right? If you have 3 children, then you can either have boy, 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 girl, boy, girl, boy, boy, girl, girl. Sometimes tree diagrams are really helpful in coming up with the sample space. Because if I know I have 2 choices for my first child, 2 choices for my second child, and 2 choices for my third child, I have 8 choices total, but coming up with them sometimes is a little difficult. So we're going to do tree diagrams for the sample space and then answer examples of the sample space. This one's the example of flipping a coin and rolling a dice. So I end up with 12 outcomes because I have 2 choices here. And eventually we're going to put probabilities on here. So this is the probability of a half, this is the probability of a half. Each one of these is the probability of a 6. Each one of these is the probability of 6. A half times a 6, each one of these are going to have a probability of a 12. So these are equally probabilities where things are equally likely to happen. We'll do game type things where certain conditions, how many different ways can I get 2 A's, for example? So if I get A, I'm done. I stop after that. If I get A, B, then I would have another probability to get either A or B. So we'll do these tree diagrams and talk about probability. Here's the cards. Here's the 52 cards in the deck that I was going to talk about. You know, what's the probability of getting a face card? The Jack, Queen, and King are considered face cards. There's 3 in each suit. There's 4 suits, so there's 12 total face cards. What's the probability of getting a red card or a heart, or sorry, a red card or a face card? You'd have to count all the red cards plus all the face cards. And so we'll do some of those overlapping probabilities. Have you guys had exposure to things like that with cards? Nope.
I can play cards.
So you've seen cards before, but never thought about the probability.
And homework.
If you ever watch poker online, they always have that probability that someone's going to win. And that's how they do it, is they know what cards have been played. They know what cards are in the deck, and they talk about what's the probability of this person getting the ace they need or the 2 they need. Sometimes their probabilities are 0. They have no chance. They don't know that, of course, so they don't know whatever one else's cards are. But
And then there's card counting.
there's card counting, yeah, using like blackjack.
Which is frowned upon.
Which is, this example confuses a lot of students because they think equally likely. But when you roll 2 dice, you only have an outcome from 2 to 12. But there's 36 different ways to do that, right? So there's 36 outcomes. This is going to add to 2, this is going to add to 3, this is going to add to 4, all the way up to the largest number being 12. So each outcome is not equally likely, right? There's only one way to get a 2. That's if you get 1, 1. But there are, oops, I need to see if I can get that back. But there are 1, 2, 3, 4, 5, 6 different ways to get a 7. So if you need to get a 7, you have a probability of 6 out of 36, which is 1 out of 6. You have a probability of 1/6 to get a 7 versus to get a 2 that has a probability of 1 out of 36. Okay, so we'll do examples up here and look at this sample space. Just because there's 12 outcomes, your sample space in this case looks like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But the probability of getting a 2 is 1 out of 36. The probability of getting a 3 is 2 out of 36. 3 out of 36, 4 out of 36, 5 out of 36, 7 out of 36, and so on. And if you add up all these probabilities, you get 36 out of 36. So this is an example of sample spaces that are not evenly distributed. So if I said, what's the probability of getting a 7? It's going to be 7 out of 36. If I say, what's the probability of getting a number less than 7? I have to count on all the outcomes that are less than 7. Right? So this diagram comes in really handy on the exam. You'll probably have to draw this, where you put the number, the blue dice, 1 through 6, the red dice, 1 through 6. Here's all your outcomes. And if I care about numbers being less than 7, that's going to be the category, this diagonal up. So I would count the number of outcomes, and I'd have my answer for probability being less than 7. So it's not always going to be equally weighted. This is probably a popular one that will be probably on the exam, where it's not equally weighted.
Will we learn percentages?
We'll go into percentages. And it's just another way to say a probability, and we'll talk about the odds of it happening, which is the same way of saying probability. So we'll get there.
Because that's kind of like when you talk about probability, people.
A lot of
just
people
talk
say,
about
yeah.
Percentages.
It's the exact same thing. Probability, percentages, and odds all mean the same thing. It's just a different way to display them. Anytime you play a game of chance, they have to list the odds of winning, which is the probability you win. And if you look at like casinos, if you look at
the slot machines, a lot of times their odds of winning are really, really small. Versus like blackjack, I think that's the fairest game in the casino, because your odds or your chances of winning are closer to 1/2. And then we'll get to expectation. If you play this game for a long period of time, how much money can you expect to win and how much money can you expect to lose? This is also games of chance. People use this to price games. They say, okay, how much would you be willing to play this game? And that's the expected value. They want to put it really close to that expected value. You know, and that's get into like lottery tickets and stuff. People don't really care to play $1, but the expected value on that, over time, the state's going to get a large amount of money, of course. People don't know the math behind it or necessarily care about the math behind it. They just care that they have a chance, and that's all they care about. If you're saying there is a chance, the chance is just so small.
You have a bigger chance of getting struck by lightning.
You do, yeah. So and then in odds, and they list that. It's a popular thing that I have side by side. Kansas City versus Springfield, the odds of being a victim of a crime. In Springfield, you have a higher chance of being a victim of a crime than you do in Kansas City. But then they also list, yeah, and I'll pull that up when we get to odds and expectations. Being able to read those, your chance of dying in a motorcycle crash. Life insurance companies use these to be able to sell you life insurance. And of course, have you ever met a life insurance company and go broke? No, they make a lot of money off this. So they have this algorithm that's based off statistics to say, listen, we're going to make tons of money off these people because the chance of them dying in the next 10 years is really, really small. So we'll go we're just kind of hitting the surface of this. There's a lot deeper use for it.
Are we having class Friday then?
We're not going to have class on Friday. So your Friday class is to get caught up on your homework. So your time in class. I will be in the teachers lounge because I have other classes I teach on Friday. If you have any questions over the homework or any of the material, I'll be in there and we can meet 1-on-1 or 3-on-1 or 5-on-1. If too many people show up, we might just come to the classroom and work on problems. But I'm not going to lecture over anything new. So
Where will you be on Friday?
Yeah.
it is on the syllabus. Let me see what room that's called. It is room. Where's my office? 360L, I think. ICE 360L. Okay. It's just, if you go in that door, there's a lot of offices, and I'm in the big one with all the computers. Okay, yeah, so I'll be in there.
Have a great weekend.
You too. I'll see you guys on Wednesday.
See you on Wednesday. Turn up.